Morning again. I'm Suzanne Dickerson. I'm the director of the South Carolina Fraunhofer USA Alliance at the South Carolina Council on Competitiveness. Welcome to our webinar series. We have been managing the alliance with the Fraunhofer network on behalf of the Department of Commerce for about 2.5 years now. And over that period of time, we've determined and confirmed demand for various technical capabilities in South Carolina, and that has resulted in a couple of advances in our strategy. One is that we realized that while most of the projects we have done have been focused on software, data analytics, digitization, and those types of digitalization advances in technology for companies, manufacturers, and entities in South Carolina. We also now have the opportunity to provide access to other areas of the Fraunhofer network. And so we've started this webinar series. Today is our third in the webinar series, and we're exposing and highlighting, shining a light on new technologies every time. So I will turn over to my colleague who is now a South Carolinian Fraunhofer person dedicated to our alliance here and the efforts that we have ongoing to help companies become more competitive. We're offering matching dollar for dollar funding for companies who would like to take advantage of that and work with Fraunhofer and some of our institutions here, academic institutions here in South Carolina. And I'll turn over to Dr. Marcel Schaefer, who will introduce today's webinar speaker.
Yeah, thank you, Suzanne. Welcome, everybody. Good morning to this Thursday webinar. Today, the topic is about advanced manufacturing, and I'm introducing now Dr. PHILIPP IMGRUND. He's head of department AM processes at Fraunhofer IAPT. Dr. IMGRUND studied material science, received his doctorate from the University of Bremen, which is a city in the very north of Germany. In fact, the city with the most charming soccer club there is. He gained vast experience in the field of powder technologies, additive manufacturing as project manager at Fraunhofer, and of course also as an R&D engineer in automotive industry. And since 2017, Dr. IMGRUND is head of Department of AM Processes at the Fraunhofer IPT in Hamburg, which is also a city in the very north of Germany. In fact, the city with the absolute most uncharming soccer club. PHILIPP has experience in the US too, so he has been here for a while. He has worked in a factory in Boston, and he can stories from there. I mean, Boston. So if you hear an accent, that might be it. Today's title is Process Innovations on the Way to Industrialization of Additive Manufacturing Technologies. And PHILIPP, the stage is yours.
Yes, thank you very much for the very kind introduction, and welcome from my side. It's a pleasure to be able to show you some of the activities of our Fraunhofer Institute here in Hamburg. And yes, I can say good morning to you, good afternoon from Hamburg. And with this, I would try to share the screen. This should be it. So I hope you can see the screen.
Yes, we can see.
I can see. Just try to get rid of the steering. Okay. Yes, so my topic today is, as Marcel already said, process innovations for industrial production of AM components. This is one of the, well, it's in principle the main mission that we have at Fraunhofer IAPT. And first of all, to make you familiar with the institute, Fraunhofer IAPT stands for Institute for Additive Production Technologies. And what you see here on this very first image is well, additive manufactured replica of the Hamburg Concert Hall, which is quite famous for its architecture. And so you already have a little insight into polymer processing, directed energy deposition, and binder jetting technologies in which we have been rebuilding this at a very small scale. But of course, we want to talk a bit more about use cases and technologies today. And I have brought with me for you use cases from the automotive sector that we are working on, use case from the aviation industry, and to finish off some words on future technologies or future sectors where additive manufacturing is heading from our point of view, from my point of view. And of course, I'll be happy to discuss with you what your view on this is. And so let's start off with a first introduction to the Institute. We have created a mission statement when we were funded around 4 years ago. So we are still a quite young institute. And we felt that lots of, well, academic institutions and also industrial companies, of course, deal with additive manufacturing, still see it as a prototyping solution for rapid prototyping. You will know it. So we defined the vision to bring additive manufacturing technologies into production and to make them viable production processes for industrial components. So this means we are dealing a lot with the correct design of the components. We're having a department which I'm leading on developing stable and quality assured processes and also the corresponding materials towards this. Of course, we have to consider automation, digitalization of processes, as additive manufacturing by itself is a digital industry. You have a data file that you send to a computer and to a machine basically, and where you print the data directly from computer, the part directly from computer data. And the last component here is also considering post-processing technologies and planning of factories, and also planning of container concepts for decentral production in the end, which is also one project that we are having with the colleagues from Fraunhofer USA. So the basis of our work is the technologies and the machine systems that we have, and the main focus is certainly laser powder bed fusion. Lots of machines, ranging from machines where we have very open access to all the steering, where we can do scientific work on the lasers, on really looking inside the process, modifying components, integrating cameras, thermal cameras, high temperature heating, and so on, optimize gas shields. But as Fraunhofer is by itself defined as an institution which should help getting components into application and getting additive manufacturing application, we also have a lot of industrial machines on which we are working together with industrial customers to qualify new materials and to transfer the technologies towards them. More recently, we have been looking at Sinter-based technologies. I will explain later on in more detail what we are doing here and what this is. And we have a third group which is dealing with polymer additive manufacturing. So very much what is considered as 3D printing. If you look at home 3D printing, fused filament fabrication, or industrial fused deposition modeling, and also powder bed processing of by selective laser sintering. So starting off with a use case from the automotive industry. I hope you can see the video. So this is a view inside the powder bed processes. So you see 4 lasers here manufacturing a part from the powder bed. And here already you see that the part is being extracted. So after the build is finished, the build chamber is being brought up, and you already see that there's a lot of manual processing still, which is not yet so good for automation. You make it slow and expensive, but you have to then cut off the part from the build platform. And here you come up with a very nice component. In this case, it is a brake caliper from Bugatti, which we have manufactured on our SLM 500 4 laser machine. So a machine very much dedicated to production of components rather than R&D. So to give you some more details about this part, at the time that we did this was in 2018. When we had this collaboration, this part was the largest titanium 6.4 part that had been printed by laser powder bed fusion. And so the idea was to come from a very traditional design to really making advantage of the possibilities of redesigning parts for additive manufacturing, designing the supports that are required so they can be extracted in a good way, and to deliver a first real use case for automotive. And in this video here, you see a brake test that has been conducted at Bugatti. So you see the brake caliper here and the brake disc here. And the speed is going up to nearly 400 kilometers an hour, which would be roughly 230 miles an hour, 250. And so, of course, it's quite impressive to see these tests. The part has passed the tests, and now if you can afford a Bugatti Chiron, you can also have an extra with the additive manufactured brake caliper. It can be ordered. So, of course, this is a perfect use case because you don't really need to consider costs so much. Yeah. So at the time, no one really, at Bugatti, costs were not such a big deal. But of course, if you want to really go into a production of parts and then to look at serial production of cars and want to make advantage of the benefits of additive for these, well, you have to look into other materials and you have to look at process cost in order to bring these down. Because here the powder from titanium aluminum is already, the price per kilogram is about 170 euro, which makes about $200 per pound. $100 per pound, sorry. So in another project we conducted together with Fiat Chrysler Automotive, we went another step forward. This is wheel suspension, which integrates a brake caliper. And our design engineers really made a nice job of including here air channels, heat shields, the brake caliper itself. And so you have the whole wheel carrier and the whole suspension here made of one part in one print in an aluminum material, which is of course way cheaper than the titanium component. And also here, I want to point you at the weight reduction of about 36% as compared to the standard manufacturing process here. And also the part size is in the range of even bigger than the caliper. So this is one of the keys from our point of view to additive manufacturing, to integrate different designs, integrate different functions, and really make a benefit out of the process that is offered. I want to briefly give an insight into our daily project work. This is from our project where we tailored an aluminum material called CustAlloy to elongation for crash-resistant automotive components. And if you see the comparison here between a standard aluminum alloy that is state-of-the-art and a new alloy, I can show this video again. You see the reason part here in the testing folding together, which is expressed by a high bending angle of the part. And so we are able to really have materials that are well qualified for the use case here. Of course, in case of an accident, you need the crash absorption and you need to pass these tests in order to be able to have the material qualified for the application. And so this is an example where we are looking at optimizing an alloy specifically for for the application it is meant to go to. Again, we have similar weight savings due to the redesign possibilities here. So very briefly touching on the story before aluminum development for additive, starting from the standard aluminum silicon 10 magnesium, which is in a range of, well, 200 to 500 megapascal tensile stress and elongations around maximum of 10 to 15%, very standard. We can go for new alloys like this CustAlloy that I just showed here, which is has a more flexibility in its mechanical property range. But also we're looking at very high strength materials, which is this PLM 905, very high strength for, well, we sacrifice ductility, but it's also a brake disc application here. And together with a company in Germany here, Fairman Alloys, we're also developing the Almighty alloy, which provides elongation up to 40% after heat treatment on a very specific tensile strength area of around 400 megapascal. So this just shows a variety that you can do with material science. As a material scientist, I have to show this, and I hope it finds your interest to some extent. Yes, so for aviation, of course, I can say this is mainly where the story of metal additive manufacturing, the success story, started. And it also started by really using the design advantages of that I have already been speaking on the automotive side. But the first parts that were there were such a component for optimizing the gas stream in the front of an aircraft. We have possibilities nowadays for reducing, I would say, sound pollution by having these inner porous structures that are dedicated for sound absorption. So the aspect of part integration I've mentioned on the FCA example already. The first example was this fuel connector for Airbus, where we integrated 14 single parts into one with a cost saving of about 50%. And of course, the topic of bionic design. So really introducing bionic features that are given to us by nature, and where we want to really look at material efficiency and saving more weight on the parts, especially on an airplane. Of course, each pound that you can save is worth a lot of dollars in terms of saving fuel and carbon dioxide. So in this sense, we had a large European collaborative project which dealt with developing bionic design and incorporating bionic design into all sorts of aircraft components. And so here you have a picture, which is a vision that was once formulated by Airbus. It's a wing-like aeroplane here. And so our project started way before this was launched, but well, we may have contributed with this project, and I want to show you some components that we designed and which we developed during this 3-year adventure that we had. And we identified from the Airbus A330 a jack actuator bracket, from the A340 a hydraulic block, and from the A350 a big T-mount fitting which supports the wings. You can see the location of the demonstrated of the components. So the actuator bracket is actuating the flaps here. The hydraulic block is here in the rear of the aircraft, and the fitting, the T-mounting fitting, is really in the inner structure of the part of the aeroplane, supporting the wing structure. And our task was to find new materials and new designs to enhance the buy to fly ratio and to reduce weight of the components. And so these are the additive manufactured parts that we ended up with, and the bionic optimized designed parts that we ended up with. I think the most impressive one is, you see here, it was a block with machined channels at first, and now it's a completely redesigned additive manufactured part with an optimization of the flow and pressure losses. And I want to just show you how the parts look in a more detail in the end after production. So this is the actuator bracket for the wings. This is a T-mount fitting also for the inner structure of the wings. Of course, in this time it's scaled. It's not 100% apart, but it's smaller because it was an R&D project. Upscaling is task of Airbus after the project. And you see the design features, the bionic design features that we have been implementing here, a grass stalk structure, and some really nice bionic radii here. So maybe you're a bit disappointed that it doesn't look that sophisticated. So it's not always the outer looks, but there's really sometimes little details that make a difference on the performance of the part. And on the whole, we managed to have a reduction of again 30 to 35% in weight on all these components. And I want to show you a little film. I hope the sound you can hear the sound. Otherwise, please let me know. Well, when I was in an airplane for the very first time, is the sound coming to you?
Yes, yes, we can hear it.
Okay, all right.
I saw on the window here how the raindrops were starting to accelerate when the machine accelerated and when it took off. And I thought, what a powerful machine this is. These powerful machines emit more than 2 million tons of carbon dioxide every single day, making a destructive impact on our environment. The need to reduce these emissions is of the uttermost urgency. Well, the goal of the Bionic Aircraft project is certainly to contribute to the reduction of emissions by applying additive manufacturing technologies, by applying bionic design principles to structural parts, and thereby decreasing the weight of the components. Bionic design takes nature as its inspiration. Living organisms are known for their remarkable material efficiency. It is through using as little mass as possible that they are able to protect themselves from physical harm.
Nature in that case gives us proven concepts throughout millions of years of evolution to give us a blueprint of what can be possible. We have the microstructure of butterflies, which will be transferred into volume infill structures that are lightweight. Honeycomb structure as a surface stiffening structure. We can make it more resistant to compressive loads. We have the brass stalk structure to improve strut-like structures and make them more resistant to bending, more resistant to compressive loads.
To automate the design process, a software toolset has been developed that is capable of parameterizing the bionic features. As a consequence, the design can be converted to a CAD model with just one click of a mouse, ready to be printed. In this case, we're working with the process of laser powder bed fusion as an additive manufacturing process. The main advantage is that we are building up the parts layer by layer, and maybe 100% of the material. Studies have shown that the powder can be recycled multiple times without any loss in quality. In order to verify the quality, a camera-based system is used to perform a 3D topographical analysis of the powder bed and the manufactured part. The 3D printed parts actuator bracket is used for the wings. Further testing techniques and repair strategies contribute towards the increased service life of these components. We are achieving up to 35% lighter components as compared to standard manufacturing processes.
Through additive manufacturing, there's so much more possible with regard to complex structures and organic designs.
We are kind of pioneers in this technology. Within the next 5 to 10 years, we will see a lot more of additive manufacturing and bionic design parts flying in air.
So I hope this was a nice insight for you, not limited to just materials and processes and the design, but you see also the aspects of quality assurance and software development that we have been tackling in that project. And if you have any more questions on that, just let me know, and I will be I'll be willing to answer as good as I can. Okay. So here are some more details on process developments that we've been conducting. Just one word on that. We've been working a lot with so-called beam shaping technology in order to enhance the processing windows and also to enhance the density of the part, and to we have been able to increase the productivity of the processes by about 25 to 30% as well, using a high strength aluminum alloy here. So this is also a bit of a more technical insight into the project task that we have been covering there. So I hope I'm not too long. Final chapter with regards to future technologies and applications. I wanted to give you some insight to sinter-based additive manufacturing. So the technologies that I have been showing until now are all about the laser powder bed fusion, so direct melting of the part layer by layer in the powder bed by the laser. And here we have a kind of a different approach. We're using either a metal powder bound into a polymer matrix and processes by filament, like the standard 3D printing process that you may know from your home printer, or by the so-called binder jetting, where you don't use a laser for consolidation, but an inkjet head that prints the ink and consolidates the powder. I have a video on that in a couple of slides. And the main advantage of this one here, of the pellet printing or filament-based printing, is you can use, it's quite cheap. You can use cheap machinery, and it's well usable for prototyping. So up to 10, 20 parts. It's way cheaper to use than laser powder bed or binder jetting. And the binder jetting process is really getting you to lower cost, about €1 per cubic centimeter in ranges of more than 1,000 parts if you want to produce higher lots, which is due to the fact that in this process you can put more parts in one powder bed, and you don't need so much post-processing to get rid of support structures than in the laser powder bed part. And so we're dealing with this process. We have the first materials at hand: stainless steels, cobalt, chrome, and titanium alloys. We can also process non-weldable materials. And so I want to also show you. So here you have a sneak peek at the process. You see the powder bed here to the left. And after the powder is dispensed, you have the inkjet printer that prints the ink into the parts. And then after this printing process, you come to curing, depowdering, debinding, and sintering. So it's a multi-stage process. Main advantage is you can really go to very tiny and precise structures. So they are in the range of 300 microns, 200 microns, the wall thicknesses here. And we have been doing one project, or we are currently working on one, which is these little towers that you see here. These are finger implants. They are used for repair of finger joints in case of arthritis. Usually you have to fix the joints, or you use some silicone implants, and here you can really adapt to the patient, to the defect for the patient. You can produce patient-specific implants in a really, really fine detailed dimension for the very first time. So these are the first prototypes made in stainless steel by this technology. And the next step for us is to transfer this also to titanium and standard titanium 6.4 or titanium tantalum and alloys for even better integration into the bone, which is on the medical side of things, the challenge. The really nice thing is that you can use such structures here, such regular structures in the CAD to design your part, and it's very much scalable. It's very easy to redesign parts with these structures here. You can have the function of osseointegration here, so that the bone is really growing into the implant very well. We're doing the mechanical testing together with colleagues from IWM, Institute of Material Mechanics, and we're looking towards automating the design for the implants by an artificial intelligence algorithm that we're developing here. So I'm not going into the details of this too much here. Just the message is that automating implant designs, really coming to patient-specific solutions with a highly precise process is the main idea here. So to finish off, final use case or final future outlook is a mobile additive manufacturing. So this is rather on larger additive manufacturing components. So how can additive be beneficial here? So of course, right now, after the COVID pandemic, of course, you see that well, the logistic chains are interrupted at many places, and the idea of decentral production of parts instead of having large warehouses which cost a lot, but producing well, additive manufacturing on demand where it's needed is a huge topic. And so our idea here is to put 3D printing units into containers that can be shipped to the where they are needed for polymers or for repair of direct energy deposition parts, or also for the sinter-based processes that I have been talking about. And so the idea at our institute is to really put the whole process chain into a container, including the model preparation, data preparation, post-processing. And I have one more video for you here on the additive mobile factory, which is using a wire arc additive process. So it's a robot controlled process. So what you see here, there's a first bottom part of the components that's going to be printed, that's being picked up. In the next step, unfortunately, you can't really film into the process, but there is a welding process going on, the wire arc welding process, in order to weld the additive manufactured part, a section, onto the part that has just been picked up here. And the third step now that you can see here is the milling process. So it's a finishing process to get the shape right here. And after this is finished, trying to get this a bit quicker now. You can make a first use test. Yeah. So this is the idea of getting really metal additive manufacturing into containers. And the same can also be done with medical parts. So this was a project where we included polymer printers into a container concept and also sterilization and sealing devices. So the idea was to produce face shields and masks and respiratory devices to support the COVID, for the fight against COVID here. And I also have a very nice video. I'm going to switch down the sound a little bit. So this is my final video, where you can see how also artificial intelligence can contribute to the additive manufacturing process. So if you're in an environment where you don't have an operator which knows about the process, the idea is we equip him with an artificial intelligence glasses, and he can see what he has to do. So you get instructions on the process you have to select, on the components that you can select, and how the parts should be printed. So he now selects, in this case, it's a breathing adapter, and he assigns it to the printer, and he assigns a face shield to another printer. And then in the next step, he can start the printer based on a virtual screen that you can see here now by him holding his hand, and he just, well, in principle, pushes a button in the air, and then the printing process starts. And you get some information on the process going on. And yeah, in the end, hopefully you come up with a quality assured and finished part. And if you have such a production directly in a container close to a hospital, that the use is clear, the part will be directly printed and can be used without further logistic operations required. And we're continuing this research, as I stated earlier, in the frame of this project that we're doing with the Fraunhofer USA colleagues, and transferring what you have just seen in principle to metal-based technologies. And yeah, we'll be able to report that, I think, in one or in a couple of months' time until the end of the year. Thank you very much. I hope I was not too long. I'm open for questions, and hope you found it interesting. Thank you.
Thank you, Philip. This was very interesting. I mean, I guess there's a pretty good use case in Germany to create a 3D printed bottle opener. I guess I could make use of that too. But I see also lots of value in the general applications, of course. I'm asking to the audience. We do have quite some time to answer any questions that you might have. So I look in the chat. I don't see any questions put in there, but now's the time to ask Philip, ask about the technology and what it can do, and maybe what it can do.
Marcel, while we're waiting for questions to come into the chat, Philip, I was wondering, this additive mobile factory concept, you know, as disrupted as supply chains around the world have been recently, must be popular. I'm thinking specifically, you know, if you could be manufacturing semiconductor chips these days, you would be overrun with demand. But do you see companies implementing that? Can you talk specifically about one case or more than one case where you have companies actually deploying that to mitigate risk in the supply chain?
We do see some interest right now from the port authorities in Hamburg, so that are in general interested in applying this for spare part production on their ships. Yeah, so if you have a container ship that's traveling for many months around the world on the oceans, and you want to, you need some spare parts, and you don't want to have a whole warehouse of spare parts with you. There are ideas around that. We have also seen queries with regards to the medical applications for face shields. So this was a project that I saw. There were partners in there, but of course, at the time being, we see lots of prototype container factories emerging. So we're also not the only ones to do that. There are applications from company Mark Forged, which are transferring this into production. I think for military applications as well. Of course, it's interesting to put that into remote areas. Yeah. So these are the targets we're looking at. Yeah. Of course, there's still a lot to do. Yeah, controlling the process after having shipped the whole equipment to another place. You have to calibrate things. So there are still research questions or logistics questions open before it will be really working. But that's our mission again, yeah, to get it to work.
Thank
Can
you.
I add to that, or can I add to the question? Like for these components, I like the idea too. So and of course I'm thinking of when could those be installed in South Carolina, for example. I mean, now I guess I understand these are prototypes. The question is, what is the roadmap? When would those be, for example, available? And are you then kind of selling these things, or is it more licensing, or is it? What's the model behind?
Well, as Fraunhofer, we are not allowed, of course, to sell parts or industrial parts, industrial machines. Yeah. So the model is, of course, to develop the technology and the logistics chain and also the control software in principle, and to license this and to sell this to an additive manufacturing company or machine manufacturer who would be picking that up. Yeah, so that's quite clear that this is a business model. So it's rather technology transfer and selling of the knowledge behind than selling the components themselves. Yeah.
And when would that be possible?
Well, in principle, for the polymer, I think the hurdles are not that high. I would say it could be done within a few months from now to deliver a complete machine, a complete container that's working. There's a complete container setting at our institute, which is a kind of a showroom for the polymer manufacturing route, and it's basically ready for a first adopter, I would say. Yeah. For the DED, I'm not the expert here. I would have to pass that to my colleague who's really in the development, but I would say let's talk about a year's perspective would be my suggestion.
I've got a couple more questions, but I would let the audience chime in too. Any questions from the audience? It's too early here.
Or it was too much in.
Yeah, people can feel free to type them into the chat and we can
Yeah,
read.
well, while they're doing, I just continue with my questions.
Yeah.
So, I mean, we already, I guess, talked about the way your group is heading towards, like, what is the big picture view for your group in the next 2 to 3 years? I guess that's towards the container thing, and I guess there are other things. I mean, you are probably very busy regarding, you mentioned the supply chain discrepancy. So what are the outlooks for your group?
Generally speaking, it's all about, or the main topic that's of in our focus right now is to how to say it, to put the single pieces of the additive manufacturing process together, so to have a complete automated process chain in the end. So it's still all about reducing the cost of manufacturing. And I briefly mentioned the topic of removing supports from laser powder bed fusion structures. Yeah, you have to cut the part from the build plate. You have to manually get rid of the support. There are first concepts to automate this, but you really need to be quicker with these processes, auxiliary processes in principle, post-processing and finishing. And you really have to bring the quality in a repeatable manner, yeah, and not have one part that is fully dense and the second part which has a couple of defects which can be disruptive to the performance of the part. So the repeatability of the processes and getting the processes to be faster and to be more stable, quality assurance in the process is a huge topic right now. And it's true for all the additive manufacturing techniques. Yeah. So we see some companies already saying, well, it takes too long, and meanwhile we're looking into cheaper technologies and we stay with our standards. So I think in the next 3 or 4 years, you really have to come up with solutions for really bringing use cases for series into the production. And that's about the digitalization of the processes, automation, including the finishing processes. Yeah, that's the main things. Yeah.
Understand. As there's still no questions there, I just continue. When would you think that this CustAlloy crash-resistant components appear in the market? So it kind of goes in the same direction. And what would be the change in cost compared to what is used in the traditional way?
Yeah. Yes, so for the high strength aluminum alloys, there's a lot of materials now being qualified, and CustAlloy is in principle, it's available on demand. Yeah, so you can order it. The composition is known and it can be manufactured, and you will be able to purchase it in principle on demand from the powder supplier that that has been in that project. And generally, materials qualification is a huge topic, because we see that the aluminum, silicon, tin, magnesium is it's not sufficient. In terms of cost, of course, there have been a lot of concepts who are dealing with scandium alloys, very rare earth alloys, to enhance the strength, but it drives up the cost. And so there's new material compositions being looked at that get rid of scandium, so aluminum magnesium based or pure aluminum silicon based, the examples that I've shown, and then you're in a price range which is again in the range of maybe 30 to 60 kilograms, very roughly, euro per kilograms, very roughly. Yeah. Instead of maybe 100 or 150 euro per kilograms for these special alloys or for titanium.
So there's room for more R&D, I hear.
There is, yeah. So the topics don't stop there, I would say.
So I suppose you would be happy to do some projects with some companies in South Carolina on that too.
Of course, yeah, we're always open for this, and yeah, so if there are specific components, use cases, or if anyone of you is already running an additive manufacturing facility and is well, needs support at some key points of the process, yeah, we will be glad to help, of course, and we're at your disposal for that.
One last question. Sorry, Suzanne. Did you get to see the rest of the Bugatti?
In fact, yes, we did. We had an event where this was presented, and so there was a Bugatti in the front of the door. Yeah, was a very nice event at the time.
Thank you, Philip.
Yes, thank you.
I was just going to say as well, since we don't see any questions in the chat, I think we can wrap it up, but I want to remind everyone that's on the webinar that if you are interested in this particular technical area and would like to have support, as Marcel mentioned already, we can, you can be in touch with me and or Marcel. We will be following up with a recording of this webinar and our contact information. Please let us know and we will get you connected with the right people, and a project like that may be eligible for matching funding from the Department of Commerce. So please let us know if you're interested in exploring that. Otherwise, I would wish everyone, I see some thank you comments now. Otherwise, I wish everyone a great day. Thank you. Thank
Okay.
Thank you all. Thank you, Philip.
Yeah, thank you very much for giving me the opportunity to talk to you, and yeah, looking forward to yeah, receiving also some feedback after the webinar, and yeah, hopefully working closer together in the future over the Atlantic. Yeah.
Sounds good.
Thank you.
Thank
Okay,
you.
thank you very much. Yeah,
Thanks, everyone.
have a good day.
Thank you.
Bye bye.